Okay, so in the last class we had discussed about the variation of this limiting molar conductivity and molar conductivity with strong electrolytes, weak electrolytes, etc. Right? Then we have learned about Kohl-Rash's law. Nandana, can you state this Kohl-Rash's law?
Limiting molar conductivity of an electrolyte at infinite dilution is equal to the sum of the molar ionic conductivities of the cations and anions.
Present. Okay, present in that. Okay, then what about the applications of this Kohl-Rash's law? Vidur, can you tell me one application?
To calculate limiting molar conductivity of weak electrolyte.
Okay, to calculate the limiting molar conductivity of weak electrolytes. Then Rijas, can you tell me the second point? Second application? Yes.
To calculate the degree of dissociation of weak electrolyte.
Okay, then what about the equation of degree of dissociation?
Alpha is equal to lambda m by lambda m0.
Very good. Alpha is equal to lambda m by lambda m0. Then what about the third application? Anna? Not audible.
Determine
Determine.
the dissociation constant of each electrolyte.
Which one?
Dissociation constant.
Okay. What about the equation? Punya, what about the equation to find out the dissociation constant? Yeah, tell me.
A is equal to C alpha square by 1 minus alpha.
1 minus alpha. Okay, today we are going to do one problem related to this Kohl-Rash's law. We have learned that we can find out the limiting molar conductivity of weak electrolytes using this Kohl-Rash's law, right? It is the sum of the molar ionic conductivities of the ions present in that solution. So we can do one problem related to this one. So we can write the question. Calculate lambda m0, that is the limiting molar conductivity for CaCl2. Okay, CaCl2. Then the lambda m0 of Ca2 plus, it is 119.0 Siemen, then centimeter square per mole. Okay. Then the lambda m0 of Cl minus ion, that is equal to 76.3 Siemen centimeter square per mole. Then you have to calculate the limiting molar conductivity for CaCl2. All of you, please switch on your videos. What's the equation of Kohl-Rash's law? Lambda m0, that is equal to nu plus, then lambda, here it is Ca2 plus, sorry, here also you can write Ca2 plus nu Cl minus lambda 0 Cl minus. This nu is the number of ions present here. Okay, so you have to look at the number of ions present in the case of calcium and chlorine. Then you can just substitute that values. Adul, can you tell me the substitution? What
1
about the
into
value of
100
new? Yes, tell me.
1 into 119
Yes, very good. Yes, then
plus 2 into 76.3.
okay, 2 into 76.3, because here there are two CaCl2, two chlorine ions there. So it is 2 into 76.3 and it becomes 271.6 Zeeman centimeter square per mole. Finished? So you can expect this example like this questions in your question paper also. And one more type of questions from this cold rashes law that we can discuss in the next class. Okay. Then the next topic is electrolysis, electrolytic cell and electrolysis. Have you completed that problem, all of you? Please switch on your videos. Finish, right? Okay, then we are moving to the next topic, that is electrolytic cell and electrolysis. In the beginning of this chapter, we have learned about the differences between electrochemical cell and electrolytic cell, right? In the case of electrochemical cell, due to the chemical energy formed in that reaction, it will be converted to electrical energy. Here in the case of this electrolytic cell, due to the applying or supplying of this electrical energy, here this chemical reaction take place. Okay, that's the process of electrolysis. By applying electrical energy, we just split the ions. So, such a cell that is used to do this electrolysis, it is known as electrolytic cell. In an electrolytic cell, the external source of voltage, that means we are applying or we are supplying this electrical energy into that cell. So, in an electrolytic cell, external source of voltage is used to bring about a chemical reaction. We have learned about the electrolysis of water in smaller classes, right? It can be converted to hydrogen ions and oxygen ions by applying electricity. That's the electrolysis of water. It comes under the decomposition reaction, okay, using electricity. So here in the same way, in an electrolytic cell, the external source of voltage is used to bring about a chemical reaction. So electrolysis, it's the phenomenon of chemical decomposition of the electrolyte caused by the passage of electricity through its molten or dissolved state from an external source. Either it is in molten state, that means in melted state, or it can be dissolved in a solution. Only the electrolysis process occurs either in molten state or dissolved state. So that's about electrolytic cell and electrolysis. Here this electrical energy, it is converted to chemical energy. Okay. So in an electrolytic cell, external source of a voltage is supplied to that electrolytic cell and a chemical reaction take place. So So electrolysis, it's the phenomenon of chemical decomposition or electrolytic decomposition of the electrolyte. It is caused by the passage of electricity through its molten state or dissolved state from an external source. Okay, then we can learn a simple example for this electrolysis. That's about two. Just 1 minute. Yes.
Here, chemical energy, like electrical energy changes into chemical energy.
Yes, yes. In the case of electrochemical cell, the chemical energy, it is converted to electrical energy. That's the main difference between electrolytic cell and electrochemical cell. Okay. Yes.
Ma'am, can you show the previous slide?
Okay, sure, sure.
Okay, ma'am.
Okay. Then the simple example for this electrolytic cell, two copper strips are dipped in copper sulfate solution. Okay, this is an example for a electrolytic cell. So both these electrodes, they are made up of copper, and the copper sulfate solution is the electrolyte. Okay, both these are made up of copper, and here it is copper sulfate solution, and one is act as anode and other one is act as cathode. When we apply voltage to this electrolytic cell, one will act as anode and one will act as cathode. Cathode, it is negatively charged, and the anode, it is positively charged. And in the case of this cathode, the pure copper, it is deposited at cathode. Okay, and the impure one, that will remain in anode. So this method is used for the purification of copper. Okay, so this is a simple example for a electrolytic cell. Here in the anode, it is positively charged, so it is oxidized, and in the case of cathode, it is negatively charged, so it is reduced. So the pure form of copper, it is deposited at cathode. So this method can be used for the purification of copper. We can also use this sodium, magnesium, aluminium, etc. Metals, they are purified using the same purpose, same method. Okay, this is clear. We just take two copper strips and one acts as anode and other one acts as cathode when we apply voltage to this two electrodes. Okay, and copper sulfate solution is the electrolyte present in this electrolytic cell. And after this chemical reaction, that means during the supplying of this voltage across these two electrodes, the pure copper that is deposited at cathode and the impure one that will remain in anode, because it is oxidizing, and the cathode, it is reducing. Okay, so that's about electrolytic cell and electrolysis. Have you completed this one?
Ma'am,
Yes.
ma'am, can you say the reason again?
for what? Purification, right?
Yes, ma'am.
Yes. In the case of anode, it is oxidizing. Okay. Oxidizing means they are just losing electrons. But in the case of copper, the pure state, that means pure copper ions from this electrolyte, it will deposited in this cathode. Here it is reduced. So always this reduction process is used in the purification of different metals that we learned in the chapter, I think 6, isolation. In the process of almost metals, reduction process is used for the purification. Okay, one of its step is reduction. So you have to remember that point. In cathode, the reduction process take place. It is negatively charged. So always the pure form of copper, it is deposited at cathode. Clear?
Yes, ma'am.
Okay. Shall I move to next one?
Yes, ma'am.
All of you finished? Then we are moving to the quantitative aspects of electrolysis. We are going to learn 2 laws that are suggested by Michael Faraday. Okay, so the quantitative aspects of electrolysis. These 2 laws, there are 2 laws here. 2 laws were proposed by Michael Faraday. So the Faraday's laws of electrolysis, first law. The first law states that the amount of any substance liberated or deposited at an electrode, it is directly proportional to the quantity of electricity passing through the electrolyte. Okay, that's a statement of the first law. The amount of any substance liberated or deposited at an electrode, it is directly proportional to the quantity of electricity passing through the electrolyte. How much electrical energy or how much electricity we are supplying to that electrolytic cell, that much amount of substance that is liberated or deposited at an electrode. Okay, that's a statement of the law. So we can represent it as M is proportional to Q. M means mass of the substance. That means the mass of the substance liberated or deposited at electrode. That is M. So M is proportional to Q. Q means the quantity of electricity or quantity of electric charge in coulombs. Okay. Coulomb is the unit of charge. It is coulomb. So M is proportional to Q, where Q is the quantity of electric charge in coulombs. Then in order to remove that proportionality sign, we are just equating this equation by adding one constant. It is Z. Okay, M is equal to ZQ. And this Z, it is called electrochemical equivalent. Electrochemical equivalent. Then we have learned that, I think you have learned it in physics, right? Quantity of electric charge, that is equal to current into time, right? Q is equal to IT. Q is equal to IT. So we can substitute this equation in the previous one. Then the equation becomes M is equal to Z into IT. Z into IT. M is proportional to Q. Then in order to remove that proportionality sign, we just add one constant. It is known as electrochemical equivalent. It is represented as Z. Then instead of this Q, we can substitute IT. Then the equation becomes M is equal to Z into IT. So this is the first law of electrolysis proposed by Michael Faraday. Is this clear? Michael, are you there? All of you, please switch on your videos.
Ma'am,
Yes.
so ZIT is the final equation.
Yes. M equal to ZIT, that's the final equation. Michael, okay. Can you please read this statement of first law?
The amount of substance liberated or deposited at an electrode is directly proportional to the quantity of electricity passing through the electrolyte.
Okay. Then, Evelyn, how can we represent this law in the form of equation?
M is equal to ZIT.
M is equal to?
ZIT.
Yeah, what do you mean by Z?
That is the electrochemical equivalent.
Okay, Z is the electrochemical equivalent. Then I?
Current.
Current. T?
Time.
Time. Here this current, it is measured in ampere and time in second. Okay, we are following SI system of unit. Current, it is in ampere and time in second. Is this clear? Rijas, have you completed?
M is for mass, right?
Yes, M for mass. That means the amount of substance liberated or deposited. M stands for mass. Okay. Shall I move to next one? Yes. Then the second law, Faraday's law of electrolysis, the second law. The amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. That means if you are supplying same amount of energy to two electrolytic cells, then the amount of different substances liberated, it will be proportional to their chemical equivalent weights. Okay? If same amount of electricity it is supplied to both electrolytic cells, then their amount of different substances liberated, it is proportional to their chemical equivalent weight. So you can write it as mass of A deposited. A means any substance. Okay, that is divided by mass of B deposited, that is equal to the equivalent weight of A divided by equivalent weight of B. That means it is proportional to their chemical equivalent weights. Chemical equivalent weights. So the quantity of electricity it is required to liberate or deposit 1 gram equivalent of any substance, it is called Faraday's constant. So the quantity of electricity that is required to liberate 1 gram equivalent. Okay, 1 gram equivalent, it is equal to Faraday's constant F, and its value is 1 Faraday, that is equal to 96,487 coulomb per mole. It is approximately equal to 96,500. It can be find out by, just 1 minute. Okay, we have find out this Faraday's constant by the charge into Na. Na means Avogadro number. Okay, charge of 1 mole of electrons into Avogadro number, and the value of Avogadro number, you know that it is 6.022 into 10 raised to 23. Then the charge that is equal to 1.6021 into 10 raised to 19. That's the charge of electron. Okay, the charge of electron it's experimentally find out. I think you have learned it in +1 in the beginning portion, that charge to mass ratio, then mass, then we have learned the value of charge. Okay, so it is a constant value 1.6021 into 10 raised to minus 19 into Avogadro number, that is equal to this 1 Faraday. So this is the second law. The amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution is proportional to their chemical equivalent weights. So here I am writing one equation, and you can tell me how much what about the quantity of electricity produced here. Okay, Ag plus electron, it's giving Ag. So according to this law, the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution, it is proportional to their chemical equivalent weights. Okay. Here you can tell me how much quantity of electricity is produced. It's according to their chemical equivalent weights. So here it is 1 electron. So you can tell me what about the quantity of electricity produced here. Anyone? Here only 1 electron. So what about the quantity of electricity produced? Punya, can you guess? Very good. It's 1 Faraday. Okay. If I am writing another one, Mg2 plus 2 electron gives Mg. Then what about this one? How much quantity of electricity will be produced? Anna? Yes? 2 Faraday. So it's very simple. According to the number of ions there, we can estimate the quantity of electricity produced. Just to multiply the number of ions with this Faraday's constant. It is 96,000. In calculations, you can use this value, 96,500. Okay. Its actual value is 96,487. But we can use this 96,500 coulomb per mole for calculations. So that's about Faraday's 2 laws of electrolysis. Shivani, can you read this second law?
Second law, the amount of different substances liberated by the same quantity of electricity passing through electrolytic solution are proportional to their chemical equivalent weight.
Okay. Then the quantity of electricity required to liberate or deposit 1 gram equivalent of any substance, it is called Faraday's constant. And 1 Faraday, that is equal to 96,487 coulomb per mole. That is approximately equal to 96,500 coulomb per mole. This is clear? Yes or no?
Yes, ma'am.
Okay. Then we are moving to the next topic. That is the products of electrolysis. Okay. Products of electrolysis. So electrolysis means due to the supplying of electrical energy, the electrolytes or the substances, they are split into its ions, right? So here we are going to learn what are products will be obtained after this electrolysis process. So it will mainly depend on the nature of material being electrolyzed and the type of electrodes being used. So this products of electrolysis, it depends on the nature of the material being electrolyzed and the type of electrodes being used. Nature of the material being electrolyzed means what about that electrolytic solution that we taken. Okay, then the electrodes, anode and cathode. If the electrode is inert, that we have learned about this platinum or gold, they will not react, but they will provide the surface for the other electrolytes to react. So they do not or does not participate in this chemical reaction. If the electrode is inert, example platinum or gold is there, it does not participate in the chemical reaction. But we have learned one example in the beginning, that's about copper. It will react in the chemical reaction. Only if the electrode is inert, it does not participate in chemical reaction. Then the products of electrolysis, it depends upon the different oxidizing and reducing species present in an electrolytic cell and their standard electrode potentials. We have learned the standard electrode potential of some elements in that electrochemical series, right? And I told you that the elements that stay above that electrochemical series, they will be undergoes reduction, and the elements that lie below that hydrogen or below the bottom space, they will undergoes oxidation. Okay, so that's why here it's told the products of electrolysis, it depends upon the different oxidizing and reducing species present in the electrolytic cell and their standard electrode potential.
Ma'am?
Yes?
When we tell the electrode is inert, means only platinum or gold?
Usually these two are used as this inert electrodes. Okay, they just provide the surface for other reactants to react. They will not involved in that reaction like the catalyst. Okay, clear?
Yes.
Okay. Inert means they will not involved in any chemical reaction. They are already stable. And in the electrochemical series, you have observed that if the electrode potential is high, okay, or they are lying at the top of that series, they undergoes reduction. And if the electrode potential is negative and they lies at the bottom of that series, they will undergo oxidation. Okay. So depending upon these standard electrode potentials of the oxidizing and reducing species, we can predict the products. Emmanuel, can you read these points?
Being electrolyzed and the type of electrode being used. If the electrode is inert, it does not participate in the chemical reaction.
Okay.
The products of electrolysis depend on the different oxidizing and reducing species present in electrolyte cell and their standard electrode potentials.
Okay. Then we are moving to the electrolysis of sodium chloride. Okay, electrolysis of sodium chloride. When electricity is passed through molten sodium chloride, I told you in the beginning, if the electrolyte is present in a molten state or dissolved state, only the electrolysis process take place. So when electricity is passed through this molten NaCl, that means melted NaCl, the sodium is deposited at the cathode and chlorine is liberated at the anode. Okay, sodium is deposited at the cathode and chlorine is liberated at the anode, and these are the two reactions take place there. The case of sodium, it is reduction because it is deposited at cathode. So sodium it gains one electron and it will become sodium atom. Sodium ion gains one electron and it will become sodium atom. In the case of chlorine, it will give electrons and it will become chlorine atom. So in the case of cathode, reduction reaction take place, and in the case of anode, oxidation reaction take place. So these are the two products that formed in the case of electrolysis of molten sodium chloride. Because only one cation and anion here, right? It's just melted, no other water molecules, or it is not dissolved. It is in just melted state. So only two types of ions there, sodium ion and chlorine ion. So sodium is deposited at cathode and chlorine is deposited at anode. Okay, but in the case of electrolysis of aqueous sodium chloride means that is dissolved in water. That sodium chloride, it is dissolved in water, and the electrolysis of aqueous sodium chloride, the products are different because there are four types of molecules there. Sodium is there, chlorine is there, then in the case of water, H plus ions are there, OH minus ions are there. Okay, so there will be some competition between these anions and cations to become oxidized and reduced. So the products will be different from this one. Here only two ions, sodium and chlorine. So one is deposited at cathode and one is deposited at anode. But in the case of aqueous sodium chloride, there are four ions due to the presence of water. Sodium, chlorine, then hydrogen ion and hydroxide ion. So there will be competition between these two ions to become reduced and to become oxidized. So the products will be different. So we can discuss that electrolysis of aqueous sodium chloride in the next class. Okay children, now is this clear for you? Electrolysis of sodium chloride?
Ma'am,
Yes, Punya.
the reaction it is written aqueous.
Sorry, it's not aqueous. Okay. Here it is aqueous means that is melted. It's in melted state. Okay. But in the case of the next one, that means that is purely dissolved in water. Here it is melted and some amount of water is produced. That's why it is aqueous. Okay.
Better to write liquid instead of aqueous.
But in the textbook it is aqueous. I will look that and tell me in the next class.
Okay.
Okay. Okay. Okay children, so we can continue this topic in the next class. So what all things we learned today? Faraday's law of electrolysis, first law and second law, along with that the products of electrolysis. Okay. Is this topic clear for you? Okay, then we can continue it in the next class. Before that, let me take your attendance. Okay children, I will mark your attendance. So thank you all. See you in the next class. Okay, bye.